Hello everyone, good morning. Myself, Dr. Shubhankar Sen, Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, invite you to the third lecture of the introductory module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall elaborate on the strong form of the governing equations, followed by discussions on primary and secondary variables. The topics that we shall discuss in today's lecture, they include the concept of fluid continuum, then different approaches for solving thermofluid problems, the fluid domain, the independent and dependent variables in thermofluid problems, the concept of strong form of a governing equation, the different strong forms of the conservation equations, and finally, the primary and secondary variables in thermofluids. The backbone of fluid mechanics is the concept of fluid continuum. By fluid continuum, we imply that the fluid acts as a continuous mass or a continuous medium. So, the fluid continuum represents a continuous medium where fluid mass is present everywhere within the fluid domain. The implication of fluid continuum concept is that at any location, at any time, fluid mass is present. For low density gases, it may be possible that the fluid mass is absent at certain location. The continuum hypothesis allows us to consider that the fluid medium is continuous so that at every location, at every instant of time, all the fluid properties, they exist and they can be defined such that the basic fluid properties such as velocity components and pressure, they can be represented as continuous functions of space and time. It is by virtue of fluid continuum concept that we can write that U equals to U of x, y, z, t, V equals to V of x, y, z, t, P equals to, I am telling in 3 dimensions. Similarly, we can write for W also. P equals to P of x, y, z, t, temperature equals to function of x, y, z, t, etc. In essence, the concept of fluid continuum enables us to use the differential and integral calculus in fluid mechanics. When we use the differential equations of second order, we imply that the dependent variables such as velocity, pressure, temperature, etc., they are present at every location within the fluid domain. In addition to that, the derivatives such as del u del x, del v del x, del 2u del x2, del 2u del y2, etc., etc., they must exist at every location within this fluid domain. So I summarize here the fluid continuum concept. The fluid continuum concept enables us to use differential and integral calculus in the fluid medium. Next, we discuss different approaches in solving a physical problem. A physical phenomenon that happens in real life, it could be solved by experimental approach. Experimental approach is the oldest approach. Subsequently, the theoretical or analytical approach was developed. After the advent of computational techniques, the numerical approach or the computational approach has been very popular in solving the fluid flow problems by solving the governing differential equations of fluid motion. Around 1960s or 1970s, a hybrid method known as semi-analytical approach, where both the analytical approach and finally the numerical approach, they were combined and the problems were solved. So the semi-analytical approach, it finds less application. So there are total 4 methods or 4 approaches by which a given heat transfer problem or a fluid flow problem can be solved. Approaches for solving thermofluid problems. The oldest approach, which is still very popular and which gives us very good results if it is done carefully, that is the experimental approach. In case of experimental approach, we don't require any governing equation, or we also don't require any boundary condition or initial condition. For the remaining 3 methods, we need the governing equations, we need the boundary conditions, and we also require the initial conditions if the problem is in the transient regime. So the second approach is the analytical or theoretical approach. In analytical or theoretical approach, we get the best solution. The best solutions mean we get closed form exact solutions, but most of the practical problems in real life are highly complex and nonlinear, and because of that, the analytical approach has been successful for a very limited range of problems. The third one, which is the foundation of current day research, is the numerical approach or the computational approach. This finite element method belongs to the third approach. So third one is the computational approach, or the numerical approach. So the finite difference method or FDM, finite volume method or FVM, and finite element method or FEM, they are examples of numerical approach or the computational approach. And finally, we have the semi-analytical hybrid approach, which finds less applications at the current time. Now, we introduce the concept of fluid domain. So, portion of the fluid continuum is identified as fluid domain, where we solve the governing equation and where we specify the boundary conditions. So, let us show an arbitrary shaped fluid domain which is occupied by the fluid medium or the fluid mass. So when we talk about the system and when we talk about the control volume, by system we actually mean we are talking about the fluid mass, and when we talk about the control volume, we actually mean an arbitrary volume through which the mass is moving or through which the system is moving. So the control volume has no connection with the mass. Control volume is just representing a geometric entity. The geometry can be deformable or non-deformable, and by system we mean that we are talking about the mass. So by system we discuss about the Lagrangian approach, and by control volume we go for the Eulerian approach. So here we are showing a fluid domain which is denoted by the symbol capital omega, and it has a boundary which should be sufficiently smooth. This boundary, we use all the boundary conditions along this boundary, and this boundary is denoted by the symbol capital gamma. So a normal at any arbitrary location to this boundary, this is denoted by the unit vector n cap. So this is the normal vector, and then it has two direction cosines in 2 dimensions. The x direction cosine is nx and y direction cosine is ny. So I have shown the angle theta, and this is the xy coordinate system. And here this boundary, it can have different segments. Boundary for the boundary segment for the Dirichlet or essential boundary condition, the boundary segment for the Neumann or natural or flux boundary condition, boundary segment for the convective boundary condition, and boundary segment for the radiative boundary condition. The closure of this domain, it means that when we talk about omega, this does not include the gamma portion. So omega and gamma together, we say that it takes the closure of the domain. So closure of the domain is denoted by the symbol omega bar, and this is the union of omega and gamma. Okay, so the boundary gamma, it is a union of gamma Dirichlet, gamma Neumann, or gamma natural, gamma convective, and gamma radiative. So gamma G, it is the portion of the boundary gamma where we talk for the essential boundary condition or Dirichlet boundary condition. Gamma H, in short, it is written as NBC, the natural boundary condition or Neumann or flux boundary condition. Gamma C, it is about convective boundary condition. And gamma R, it represents the portion which is exposed to the radiative boundary condition. So in the coming classes, we shall solve example problems of all the boundary conditions that we have mentioned here. We shall just derive the weak form and then we shall solve certain problems. Here, we can show that the boundary portion, this particular portion, we can denote it as gamma G, the Dirichlet boundary portion. This portion we can denote as gamma H, the Neumann boundary condition portion. This we can denote as gamma C, the convective boundary condition portion, and the remaining portion, this one, we can denote it as subject to the radiative boundary condition. This is the gamma R boundary condition. So if we go to one dimension, we can consider a one-dimensional rod which is of length 1 unit. So it has two boundaries. One boundary is located at x equals to 0 and then another boundary is at x equals to 1. So for this particular problem, we say that excluding the boundary, if we exclude the boundary, then the remaining portion that represents omega, and then these two boundary points x equals to 0 and x equals to 1, they represent our gamma. So when we consider the closed domain, so we can write it as omega equals to, so this domain where x is varying from 0 to 1, here the domain omega, it is an open interval. In that open interval, the two extremities 0 and 1, they are not considered. If we want to close the interval, then the notation is in this manner shown, that these two extremities, they are part of omega bar. So when we write omega bar, we close it, we write it as 0 and 1, they are within the closed interval. So there should be no confusion between omega, gamma and omega bar. And as I repeat here, that gamma should be sufficiently smooth boundary. Now we discuss about the independent and dependent variables in thermofluids. So the independent variables in thermofluids and any other variable problems are the spatial coordinates and the temporal coordinates. So x, y, z and time, they always act as independent variables. The primary degrees of freedom or primary unknowns are known as the primitive variables in a fluid flow problem. The primitive variables in fluid flow problems are density rho, velocity vector v bar, which we can write in terms of components q, v and w, then pressure or static pressure and temperature. These are known as the primitive variables or the primary degrees of freedom. Primitive variables or primary degrees of freedom, primary DOFs. Now we have some thermodynamic properties. These thermodynamic properties are pressure, temperature and density. These are the major thermodynamic properties. Major thermodynamic properties. Now we have thermal conductivity K and we have the dynamic viscosity mu. These are known as the transport properties. Transport properties. Then the specific heats at constant pressure and constant temperature, constant volume. So Cp, Cv, total energy, enthalpy. These are also thermodynamic properties. These we classify under other thermodynamic properties. Other thermodynamic properties. So when we solve these conservation equations for mass, momentum and energy by using any of the discretization techniques such as finite difference, finite volume or finite element, our fundamental unknown quantities are the primitive variables. So for incompressible flow, our unknown quantities are U, V, W in 3 dimensions as well as pressure and temperature. In most of the cases, we consider thermal conductivity, dynamic viscosity or the specific heats as constants. Next, we introduce the concept of strong form of a differential equation. So, the governing equations, when we write in the continuum domain, they are known as the exact equations or are the continuum equations. These equations are always written in the differential form. So, in our fluid mechanics problems or the thermofluid problems, the maximum order of these continuum equations are 2. So, momentum equations and energy equations, they are of second order. So, here by strong form we mean that the continuum or exact form of the differential equations along with the boundary conditions, along with the boundary and initial conditions. So, when we write about the strong form, we write the original governing equation without any modification. We say that this is the exact equation and we write the exact boundary conditions specified on gamma and exact initial conditions. This set of boundary conditions, initial conditions and the continuum differential equation, they construct the strong form of that particular governing equation. So let us consider heat conduction in multi-dimensions, maybe 1D, 2D, 3D, it does not matter. So let us consider steady state heat conduction. So we write this equation by Poisson's equation, write this case as K del square T plus Q equals to 0. This is the celebrated Poisson's equation. This represents a boundary value problem and this is an elliptic partial differential equation and this is for steady state heat transfer. Now this particular equation, this is valid here on this domain omega and it has boundary. So this boundary, let us consider, it has 4 segments. This first segment is gamma Dirichlet, the second segment is gamma Neumann, the third segment is gamma, let us say gamma convective, and the fourth segment is gamma radiation. And then this overall we have this gamma, and here when we write the continuum equation, so we write that this equation is valid at any location within the domain and this is a second order equation. It means that temperature is the degree of freedom or temperature is the unknown quantity and here the small q is known as the source term. If it is negative then it could be sink term. So this temperature, it has to be continuous at every location. It means that at any point we have the value of temperature and the distance between 2 points is infinitesimal or infinitely small. When we go to the continuum level, we talk about the infinitesimal distance. So the temperature is constant and if we look into the derivative del square T, we have del T del X, we have del T del Y we have del 2t del x2 and we have del 2t del y2, all the partial derivatives in 2D. So it implies that when we write del 2t del x2, it means that del 2t del x2 must exist at any location within the domain. So accordingly, we can say that temperature is continuous at any location. Del t del x, del t del y, del 2t del x2 and del 2t del y2, they must have values at any location within the domain omega. It means that the quantity capital T must be at least twice differentiable within the domain. So this requires a higher order differentiability condition on the degree of freedom. Let us write the strong form for the steady state problem. For a steady state problem, we don't require any initial condition. So the strong form is written as strong form of Poisson equation. This is Poisson equation which is written on the left side. K del square T plus Q equals to 0 on omega. So this is about the governing equations. Now let us write the boundary conditions. So here we write that temperature equals to given, some value is given, so we indicate it by small g on gamma g. So on the Dirichlet boundary, temperature is given. On the Neumann boundary, we have minus K del T del N equals to H bar. So value of heat flux is specified along this Neumann boundary. So we say that this is given along this Neumann boundary gamma H. Similarly, for the convective boundary, we can write minus K del T del N equals to convective heat transfer coefficient H into T minus T infinity on gamma C. And finally, minus K del T del N equals to epsilon sigma T to the power 4 minus alpha QR dot on gamma radiative. It means that this forms the strong form of the Poisson's equation where we specify all the types of boundary conditions possible along with the governing equations. So here epsilon is the emissivity of the surface of the boundary, alpha is the absorptivity of the same surface, QR dot is the radiation received by the surface, and this T, this capital T or this capital T, they are the temperatures on the surface. These are unknown quantities, and T infinity is the free stream temperature. So I must mention that at the last expression where we are writing in the Stefan-Boltzmann constant sigma, temperature is in Kelvin. So in this problem, temperature must be represented in the Kelvin scale. Okay. Our next topic is the strong forms of the conservation equations. So here we have already shown how to write the strong form for a given fluid mechanics problem or a heat transfer problem. We have to write the governing equation on the domain where it is valid, and then we have to write the boundary conditions where we are having the different types of boundary conditions on the portion of the gamma. So now here mostly we shall show the governing equations without the boundary conditions. We shall consider the basic conservation equations, continuity equation or conservation of mass. Then we shall go for the momentum equation, linear momentum conservation, which is popularly known as the Navier-Stokes equations of fluid motion. And finally, the first law of thermodynamics, which is known as the energy equation. So first, what we do that if we consider that capital phi is a transport property, when the fluid is moving, when the fluid is traveling from here to there, it is actually carrying with it the mass, momentum, energy and species. These are being transported by fluid motion and also by the transport coefficient such as thermal diffusivity or the molecular diffusivity, means that is the kinematic viscosity. So here capital phi represents an extensive property which is a function of mass. Then we define its intensive counterpart. So capital phi is extensive property. Extensive property. Capital phi represents extensive property if small m represents system mass or fluid mass. So whenever we talk about the system, we imply that we are talking about the mass. Then small phi, it is d capital phi dm or intensive property is extensive property per unit mass equals to intensive property. So small phi represents the intensive counterpart of the extensive property capital phi. So with small phi as the degree of freedom, so small phi, let us take it as it is a function of space and it is a function of time. This is the degree of freedom or primitive variable, which is unknown quantity. This is the unknown. Now we have a generalized transport equation. This equation is in vector form. So in previous classes I told you that a vector is a coordinate free identity. So this equation which I shall write now, this will be written in the vector form or coordinate free form. So this general transport equation, general or generic transport equation, generic transport equation in vector or coordinate free form is del t of rho phi plus divergence of rho v bar phi equals to divergence of capital gamma grad phi plus s phi. So here I shall mention that this capital gamma, even though I am using the same symbol, this capital gamma, this is diffusion coefficient, this is not the boundary. Okay, I have used the same symbol for denoting the domain boundary. So here we are using gamma. It is not for the domain boundary, but this is for the diffusion coefficient. So better I use a subscript d, gamma d, to segregate it from the domain boundary. In this expression, this is a conservation equation. Okay, so rho is the fluid density, v bar is the fluid velocity, gamma d is the diffusion coefficient, and s phi is the source term or the sink term. If s phi is positive, it is a source term. It is whatever the property is transported, that property is generated by this term. If it is not generated, but if it is removed or eliminated, then we say it is a sink term. So this is a balance of four terms, two terms on the left hand side, two terms on the right hand side. This first term is known as the unsteady or temporal term. The second term is known as the convective term. The third term is known as the diffusion term. And finally, the last term is known as the source or sink term. Now, if we look in steady state, this unsteady term will be 0 in steady flow. Now, in this convective term, the term within the bracket rho v bar phi, this is the flux of phi. So rho v bar phi, this is the convective flux of phi. This is the convective flux of phi, and gamma d grad phi, this is the diffusive flux of phi. So when the fluid motion is very powerful, this convective term, this is very important, and in absence of fluid motion, the flow becomes diffusion dominated. So convection and diffusion, these are the two primary modes of transport. Now this rho v bar phi, here this quantity v bar, this is known as the convective velocity. Okay, so I just write it. This v bar is known as convective velocity. Now this particular format, this particular appearance where the terms are written in the divergence form, divergence of convective flux and divergence of momentum means diffusion flux, we say that this is the strong conservative form of the governing equations. So whatever the fluid flow phenomenon is happening, whatever the terms are present, these terms will belong to either of these four terms. No more terms are possible other than these basic four terms, and this is the basic equation or the generic equation. We can say that from this equation we can derive the mass conservation equation, we can derive the momentum conservation equation, or we can derive the energy conservation equation. So this is the generic transport equation. This equation is particularly useful when we deal with the finite volume method, because in finite volume we work using the balancing of fluxes. So finite volume method is an integral based method like the finite element method. And then when we perform the integration, when these fluxes are taken as a divergence, this integration becomes very simple. So because of this particular format is suitable for the finite volume method. When we use the finite element method, we don't use this format, but the basic governing equations are easily derivable from this particular generic equation. Now let us consider derivation of the continuity equation from this generic equation. Before that, let us write this equation using the tensor notation. So we can write it as, and another thing I mentioned that this phi can be a scalar quantity or this phi can be a vector quantity. There is no restriction on this. Okay. So it is in tensor form, in tensor or indicial form. This equation becomes del del t of rho phi plus del del xj of rho uj phi equals to del del xj gamma del phi del xj plus s phi. So this is ultimately a scalar equation. So there should be no free index. Because of that, in the left hand side, we have J repeated in the convection term. There is no free index in the convection term. Similarly, there is no free index in the diffusion term. It means that this is a scalar transport equation. Now we go for the derivation of the continuity equation from the generic basic transport equation. So for the continuity equation, our extensive property is mass, the fluid mass. So this is for derivation of the continuity equation with capital phi as mass. We can write it small phi equals to d capital phi dm equals to dm equals to 1. Now if we go to the generic equation and if we put the value of phi, then we find it putting in the generic equation, we get del del t of rho into 1 plus divergence of rho v bar into 1, it means it is rho v bar, equals to divergence of gamma gradient of 1, gradient means derivative of 1, plus there is no source of mass, there is no sink of mass, so it is 0. Now this gradient of 1 is equals to 0. It means that the right hand side is 0. So we can write it as, this is as del rho del t plus divergence of rho v bar equals to 0. This can be written in tensor form del rho del t plus del del xj of rho uj equals to 0. So this is the generalized continuity equation in strong conservative form. So we can have certain simplification from this equation. So we can write it as del rho del t plus divergence of rho v bar equals to 0. Now we can expand this term as del rho del t plus gradient of rho dot v bar plus rho into divergence of v bar equals to 0. This we can write as del rho del t plus v bar dot gradient of rho plus rho into divergence of v equals to 0. This gives us del rho del t plus v bar dot del into rho plus rho into divergence of v equals to 0. This portion, this can be written as del del t plus v bar dot del operating on rho plus rho into divergence of v bar equals to 0. This is the material derivative operator. This is the material derivative operator d dt. So we can write it as d dt plus rho into divergence of v bar equals to 0. Now, if rho is constant, then we say that it is incompressible fluid. Okay. So if the density is constant, this term, this material derivative term will be 0. So for incompressible fluid, we get that divergence of V equals to 0. And it is also known that for incompressible flow also, divergence of V equals to 0. So the zero divergence condition for incompressible fluid, it can be proved taking the help of the material derivative operator. So this is the continuity equation which we got from the generic transport equation. Now let us go for the momentum equation. Momentum equation. So these are the strong forms. As I have told you that I am not showing the boundary conditions. I shall summarize it at the end of first part. So I am showing only the governing equations. So continuity equation we have already shown in vector form, in tensor form. This is a scalar equation, and then we have the momentum equation, which is a vector equation. So we have three conservation equations: mass conservation, momentum conservation, energy conservation. Mass conservation and energy conservation, these are scalar quantities. Because of that, we have only one continuity equation and we have only one energy equation. But momentum is a vector quantity. Because of that, we have the Navier-Stokes equations have three components. Okay, so for momentum transport or momentum conservation equations, or here momentum means linear momentum. Linear momentum equations are Navier-Stokes equations of motions. Equations of fluid motion. Here we take that capital phi is the momentum of the fluid. So it is mv bar. Then we get small phi equals to ddm of mv bar. So this comes simply as v bar, and we take the source term as the pressure gradient term. Pressure gradient term acts as a source of momentum transport, plus the body force term. The body force is that force which acts from distance without direct contact. So body force examples, very common example is the gravitational force, and we also have the electromagnetic force. These are the forces which act from distance. So in this source term, we have two forces: pressure gradient force. This is actually a surface force, and the second part we have the body force. Okay, so both are considered as the source term. So if we substitute these quantities in the generic basic transport equation, our basic transport equation was del T of rho phi plus divergence of rho v bar phi equals to divergence of gamma d grad phi plus s phi. So we consider the diffusion coefficient as the dynamic viscosity. So here if we substitute, we get del T of rho phi. Phi is v bar, rho v bar plus divergence of rho v bar equals to divergence of mu into gradient of v bar minus gradient of pressure plus rho f bar. So this equation, this is one form of the Navier-Stokes equations of fluid motion. If you look into this expression, here we have the momentum flux term rho v bar. So this is the momentum flux term which we discussed in the chapter 2 or lecture 2 on the tensor portion. So we told that here v bar and v bar, we can write it. It means that it is the outer product of v bar with itself, or it is like rho v bar transpose. Then it gives us a 3/3 matrix. So when we write the outer product, we can use this particular symbol, the cross mark within the circle, or we can simply keep them alongside. We can just, if we simply keep them beside one with another, but this is not commutative, we say that we are talking about the outer product. Okay, so if we simply keep v bar, and if we keep v bar, outer product symbol v bar, they both represent the same thing. So this is the strong conservative form of the momentum equation. Now, the most popular form which we use in the Navier-Stokes equations that comes from the finite element formula that is used in the finite element formulation, that is known as the stress divergence form. The stress divergence form of NS equation. NS means Navier-Stokes. The stress divergence form of the Navier-Stokes equations. So we write here del T of rho V bar plus divergence of rho V bar equals to divergence of sigma plus rho F bar. So this is the most popular form which we use in the finite element method for deriving the weak form of the Navier-Stokes equations, because in the previous class we have shown this simplification of the stress divergence term. If we simplify in this manner, if we perform the integration, we shall show at the end of this towards the end of this course, we have 2 lectures on Navier-Stokes equations. That time we shall show that we need the secondary variables, the surface traction force as the secondary variable, as the force vector. So those will only come if we start our derivation taking the divergence sigma format. Okay, so this is a compulsory format for using in the finite element method. Now this divergence of sigma I have shown in the previous class. So this is the vector. So it is del sigma ij, del xj, and I have already told you that momentum equation is a vector equation. So I is the free index and j is the repeated index. So easily we can expand this term. So this will be del sigma ix del x plus del sigma iy del y in 2 dimensions. So we can even write it as del sigma, for x momentum equation, del sigma xx del x plus del sigma xy del y. Now let us go to the stress tensor sigma. This is known as the total stress tensor. This sigma is known as the total stress tensor at a point. Total stress tensor at a point. So this stress tensor, it has 2 parts. One is the ideal fluid flow part and one is the viscous fluid flow part. The ideal fluid flow part is known as the isotropic portion. This we shall write as pressure into identity matrix, plus it has the real fluid flow portion, the viscous part. So that is mu into gradient of velocity plus its transpose. So gradient of velocity is transpose. And then we have the second viscosity lambda into divergence of V into the identity tensor. So this particular expression sigma equals to minus pi plus mu into gradient of V, mu into gradient of V plus gradient of V transpose plus lambda into divergence of V into the identity matrix. So these 2 parts are known as the first part is known as the isotropic stress and the second part is known as the deviatoric stress. By isotropic stress, we imply that at a particular point, by Pascal's law, for a stationary fluid or for a moving fluid, pressure from all the directions is constant, it is same. So pressure is the isotropic stress. So pressure is a scalar quantity, means the stress tensor, it is a sigma is a second order tensor, but pressure is a scalar quantity. When we are writing a second order tensor on the left hand side, in the right hand side, every term must represent a second order tensor, but pressure is a scalar. So to write it in second order tensor form, we introduce the Kronecker delta operator capital I, which is a second order tensor and which makes the isotropic stress as a tensor part. Then we have the deviatoric stress, the viscous stress, which is direction dependent. So because of that, we are using this as a deviatoric stress, which shows deviation with respect to direction. It has 2 parts. The major portion, which is conventional portion, we say that this is the dynamic viscosity into the velocity gradient and the velocity gradient's transpose. This gives some kind of measure of strain rate. So viscous coefficient into strain rate, that is the stress. So this is the second order stress, and the last portion is lambda into divergence V into the Kronecker delta operator. This lambda is a secondary viscosity which is known as the second coefficient of viscosity. You know that this comes from Stokes' hypothesis that lambda equals to a function of mu. We take it as lambda equals to minus 2/3 mu. So in most of the problems, we deal only with the mu, not with lambda. So this stress tensor expression, if we write in the tensorial notation, then we can write it as sigma ij equals to minus p into delta ij plus mu into del u I del xj plus del u j del xi plus lambda into del u k del xk into delta ij. This is the same expression with the previously we wrote in the vector expression, and then we are writing in the tensor notation. So this sigma we can write as sigma equals to minus p into delta ij plus tau ij. Okay, so this entire viscous stress is written in terms of the tau ij portion. So first part is the inviscid stress and second part is the viscous stress. Now if we previously we have written the Navier-Stokes equation as del t of rho v bar plus divergence of rho v bar equals to divergence of sigma plus rho f bar. If we write in the indicial form, then we can write it as del t of rho ui plus del xj of rho ui uj equals to del sigma ij del xj plus rho fi. This is the ith momentum equation. Okay, so this rho ui uj is a second order tensor. Now this del sigma ij del xj, this gives us del xj minus p into delta ij plus tau ij. This gives us minus del p del xi plus del tau ij del xj. Okay, so in the Navier-Stokes equations, actually we deal with the stress divergence form of the governing equation, and then if we simplify it, we have simplified versions we can write in terms of the primitive variables. Okay, so if we write in terms of the primitive variables, or if we write in this term, then suppose for I equals to 1, we can write this equation as, this will be the x momentum equation, del t of rho ui plus del x1 of rho u square. Del x1 means del x, then del y of rho u v plus del z of rho u w equals to minus del p del x plus del tau xx del x plus del tau xy del y plus del tau yz xz del z plus rho fx. So this is the x momentum equation which we get from the generic form by substituting I equals to 1. So similarly, if we put I equals to 2, we get the y momentum equation, and I equals to 3 gives us the z momentum equation. So something I just forgot at the beginning to mention, that all the conservation equations which we write, I have written already 2 equations, continuity equation and momentum equation. I emphasize here that in fluid mechanics, we use the Eulerian approach. When we discuss about the Eulerian approach, we focus on the points and not on particles. So particles are discussed in solid mechanics and points are discussed in fluid mechanics. Because of this, I emphasize that all these equations are written at a fixed point within the fluid domain. So these are the strong forms, these are the continuum equations. These continuum equations are valid at any locations within the domain. Since we are using the fluid continuum hypothesis, velocity, pressure, temperature, everything, they are defined at a point, and because of that, the second derivatives, first derivatives, all the partial derivatives, they are at least existing everywhere within the domain, and so the combination of them, they are giving us the governing equations at any point within the domain. Now we go for the, here I have less space here, so I did not discuss about the energy equation. So here itself I shall discuss the energy equation. The space is less here, so I just separate this in two portions. So in the bottom portion, I shall write the energy equation, and these primary and secondary variables I shall discuss after this. So let us go for the energy equation derivation from the basic transport equation. For the energy equation, let us take capital phi equals to total energy. So that is specific energy into the mass. Then we get small phi equals to dE dm equals to E equals to the specific energy equals to specific enthalpy plus kinetic energy per unit mass plus the potential energy per unit mass. We ignore the last two contributions from the mechanical energy and we take it as E is approximately equals to H, so that phi is approximately equals to H equals to Cp into temperature, where T is in Kelvin. Okay, so we take gamma equals to K by Cp, and we take the source term S phi as the source term, volumetric source term, plus the viscous dissipation term, we denote it by the symbol beta. Now from that equation, del T of rho phi plus divergence of rho v bar phi equals to divergence of gamma grad phi plus S phi. We can write it as del T rho H is Cpt plus divergence of rho v bar Cpt equals to divergence of gamma means K by Cp, then gradient of phi is Cpt plus our source term is Q, it is Q plus beta. So this gives us del T. If we consider rho and Cp as constant, we can simplify it as rho Cp del T plus V bar dot del. This is the advection term. In case of energy transport, the convection term, it is known as the advection term. Then it gives us K del dot del is del square T plus Q plus beta. So beta is gradient of velocity into double dot product of the stress tensor. So I told you that energy is a scalar quantity. So energy equation must be a scalar equation. Every term of the energy equation should represent a scalar. So gradient of V is a second order tensor and sigma is a second order tensor. They should give us a scalar. It is only possible if we take a double dot product. Single dot product reduces the order by m plus n minus 2. I told in the second class. So two dot products will reduce the order by 4. So total fourth orders, 2 from gradient V, 2 from sigma, they will be giving us a zeroth order tensor or a scalar quantity. Okay, so this is the energy, this is one form of the energy equation. Now if we consider a steady state heat transfer, then this del T will be 0 for steady state heat transfer. This is in coordinate free form. Coordinate free form means this can be valid in Cartesian coordinate form, cylindrical coordinate system, spherical polar coordinate system, or any other coordinate system. And here for unsteady state, this is for the unsteady state. For steady state, del T will be 0. If the fluid is not moving in a static fluid or in a solid medium, we say that V bar equals to 0 in static fluid. So if the advection is absent, then the left hand side of this equation becomes 0. Then we say that we have K del square T plus Q plus gradient of V double dot sigma equals to 0. Now this gradient of V double dot sigma, this is an insignificant term. In conventional flow, we ignore it, we discard it. So we are left with K del square T plus Q equals to 0. So this equation is known as the Poisson's equation. So this is the Poisson PDE. This is Poisson equation. Now, if we ignore the source term Q, then the final equation is K del square T. So K del square T equals to 0 is known as the Laplace equation. Now, Poisson equation and Laplace equation, they are examples of boundary value problems. They are known as BVP or boundary value problems. These are examples of elliptic PDE, elliptic partial differential equation. When we got the generic equation, energy equation, this equation is parabolic partial differential equation. So, the heat diffusion equation, if it is unsteady, then it is a parabolic partial differential equation. If it is a steady state equation, it reduces to elliptic partial differential equation. So, elliptic partial differential equations are known as boundary value problems or equilibrium problems or Jury problems. Parabolic partial differential equations as well as hyperbolic partial differential equations are known as marching problems. So currently we are discussing about the parabolic partial differential equation. So this is an example of a marching problem. This is an initial boundary value problem where we need the boundary conditions as well as initial conditions. So here I have shown the strong form of the classic equations like conservation of mass, linear momentum, and energy. So boundary conditions in one example problem at the beginning itself I have shown what will be the boundary conditions for Laplace or Poisson's equation. We can extend those conditions for the fluid flow problems, Navier-Stokes equations coupled with the continuity equation. So the next topic is the primary and secondary variables in thermofluids. So the primary variables, already I have mentioned that the primitive variables, they are known as the primary variables, and the secondary variables are the fluxes of the primary variables. So primitive variables are the primary variables that we solve using FEM. And EBC or Dirichlet boundary condition is defined on them. Fluxes or primitive variables give the secondary variable, and Neumann boundary condition works on them. So we have two conditions, two variables, primitive or primary variables and the secondary variables. Now, by taking fluxes of the primitive variable, you can get many expressions, but all of them, they do not necessarily represent the secondary variable. So there is a condition of defining the secondary variable that we identify from the weak form of the governing equation. When we discuss the weak form in the coming weeks, then it will be clear that how the secondary variables are selected. For every primary variable, secondary variable will exist if the secondary variable is, if the governing equation is at least of second order. It means when we go for the Laplace equation or Poisson equation, it is a second order partial differential equation. Because of that, we have a secondary variable. But if we go for a first order equation, then we have only primary variable, but we don't have any secondary variable. So here, equation wise, I show the primary and secondary variables. Okay. First is Laplace, Poisson, or unsteady heat conduction. So the primary variable is T for temperature, and secondary variable is minus K del T del N. It is minus K into N cap. So del N is the directional derivative I mentioned in the previous class. So it is K into n cap dot del into t equals to minus k nx del del x plus ny del del y plus nz del del z operating on temperature. So n cap dot del is the directional derivative. So minus k del t del n is the heat flux. So this heat flux is the secondary variable for the Laplace equation, Poisson equation, or unsteady heat diffusion equation. It means for the energy equation, heat flux is the secondary variable and temperature is the primary variable. Now let us consider the first order wave equation. So this previous case, these first two are elliptic. The second one is parabolic. So whether it is elliptic or parabolic, it does not matter. Primary and secondary variables do not change. Now, the second example is for the first order wave equation. In first order wave equation, the equation is del u del t plus c del u del x equals to 0. This is a hyperbolic partial differential equation. Hyperbolic PD. So c is the speed of wave. So c can be positive or c can be negative based on in which direction the wave is moving. So in this case, the primary unknown quantity is u. So the Dirichlet boundary condition will be given on u velocity component. If it is the velocity, then u will be the quantity. Now if you look, this is a first order. The wave equation of first order is a first order equation. Okay, so it does not have any secondary variable. It does not have any secondary variable because secondary variable will be like del u del n. But here our equation order is 1. So equations order and boundary conditions order, it cannot be same. It should not be same. Because of that, for first order wave equation, there is no secondary variable. Now let us go to the second order wave equation. That is also an example of hyperbolic PDE. So this equation is del 2u del t2 equals to c square del 2u del x2. Here also u is the degree of freedom or u is the primary variable. Now if you see here, this is a second order equation, so it can have a first order secondary variable. For this particular case, the secondary variable is c square n cap dot del operating on u or c square del u del n. So for the second order wave equation, we can define a secondary variable. Similarly, space is not there. I try to fill it here. Now we go for the convection diffusion equation. For the convection diffusion equation, the equation is del u del t plus c del u del x equals to nu del 2u del x2. So in this case, what we see that our primary degree of freedom is u and secondary degree of freedom is nu into n cap dot del into u. So it is nu del u del n. So this is the secondary variable for the convection diffusion equation. Primary and secondary variables for Navier-Stokes equations. So here Navier-Stokes equations, these are having mixed behavior. We say they are elliptic parabolic PDEs. So they are primary and secondary variables. Primary unknown is u, v, w, p. So this velocity and pressure, thermodynamic pressure these are the primary unknowns and these are the primary variables. So we specify the Dirichlet or essential boundary conditions on velocity and pressure. Mostly we use them for the velocity components, and the secondary variable is the surface traction force. So this is denoted by the symbol H bar. H bar equals to n cap dot sigma. So the normal projection of the surface stress, so we have it as Hj equals to Ni sigma ij equals to Nx sigma xj plus Ny sigma yj. This is in 2 dimensions. So if we expand it here, then we can write it as Hj equals to Nx sigma xj plus Ny sigma yj. This gives us Hx equals to Nx sigma xx plus Ny sigma yx equals to Nx minus P plus 2 mu del u del x plus Ny into mu into del u del y plus del v del x, and Hy equals to Nx sigma xy plus Ny sigma yy equals to Nx into mu into del u del y plus del v del x plus Ny into minus P plus 2 mu del v del y. So in 2 dimensions, these are the expressions for the surface traction forces. Now, if we consider a fluid flow problem, so surface traction, actually it is defined here. This is the exit boundary. This is the direction of fluid flow. Then we say that we use the traction-free boundary condition. So here we give the essential boundary conditions or Dirichlet boundary condition. So by traction free, we indicate that Hx equals to 0 and Hy equals to 0. Along this surface, we have Nx equals to 1, and when Nx equals to 1, Ny has no value. So if we look here, for Nx equals to 1 and Ny equals to 0, Hx will be Nx equals to 1 means minus P plus 2 mu del u del x, and Ny is 0, it gives us 0. So Hx equals to minus P plus 2 mu del u del x. Now at this exit boundary, we consider the 0 gauge pressure, and in incompressible flow we use the gauge pressure. In compressible flow we consider the absolute pressure. Okay, so here the P is the gauge pressure, so it is a 0 gauge pressure. So we take it as 0 plus 2 mu del u del x. Now Hx equals to 0. This gives us Hx equals to 0 gives us del u del x equals to 0. So when we go for the finite difference or finite volume methods, we use del u del x equals to 0. We don't write Hx equals to 0. But when we go for the finite element method, we write it as Hx equals to 0. Similarly, if we go for Hy equals to 0, that can also be simplified as Nx equals to 1. So it is mu into del u del y plus del v del x plus Ny is 0, so it is 0. Now, along this vertical line, the u velocity is constant. So along this vertical line, this u velocity, it recovers. Because of that, this del u del y is 0, and then we are left with mu into del v del x. So mu del v del x equals to 0. This gives us Hy 0 gives us del v del x equals to 0. So these are the simplifications of the traction-free boundary conditions when you deal with finite difference or finite volume methods. So in brief, these are about the strong form, primary variables, secondary variables. I conclude today's lecture. Today we have discussed the strong form of the governing equations in relation to thermofluids. We have 3 basic conservation equations. conservation of mass, conservation of momentum, and conservation of energy. So these equations are maximum of second order. So the first point is that in thermofluids, maximum order of strong form is 2 for the Navier-Stokes or the linear momentum equations, as well as the energy equation. The Laplacian operator del square, this is having the highest order in both of these equations. This Laplacian operator indicates that the derivatives del x, del y, del 2 del x2 and del 2 del y2, if they operate on a variable, for example temperature, then del t del x, del t del y, del 2t del x2, del 2t del y2, they must exist everywhere within the domain. So there is stringent continuity requirement of all the derivatives which are written here. So temperature itself must be continuous, del u del x, del u del y, they must be continuous, and del 2u del x2, del 2u del y2, at least they must exist throughout the domain. So this is the stringent requirement in case of a strong form. We have introduced certain operators during the strong form derivations. So these operators are the Laplacian operator. I have just mentioned about this. Del square operator, del dot del. This is a symmetric operator. So this I mentioned that Laplacian operator is a symmetric operator. So this Laplacian operator gives us a symmetric matrix when we discretize a governing equation that is having Laplacian operator. For example, if we write the energy equation, the Poisson's form or the Laplace's form, then if we generate the matrix equation system AT equals to B, blindly we can tell that capital A must be symmetric. And we have already discussed that capital A is also positive definite. Now, if we go to the fluid flow operator, the convective operator, this operator is V dot del. Okay, and already we have mentioned that V bar dot del is not equals to divergence of V. This is not divergence operator. This is V bar dot del. This is the convective operator. This operates on the velocity vector, and this operator V bar dot del, this is an asymmetric operator. Because of presence of the convective operator, the matrices which will be generated from fluid flow problems, they will be by default asymmetric. And the convective term in the strong conservative form, it was written as divergence of rho V bar V bar. Here we already mentioned that V bar and V bar, they are in outer product relationship. So this is a second order tensor, and divergence of a second order tensor becomes a first order tensor or a vector. The Navier-Stokes equations, they are conservation statement of linear momentum. So ultimately, they are a vector. Navier-Stokes equations are vector. They are vector equations components. So this divergence of a second order tensor, it is a vector. So we have consistency. And then V bar dot V bar, this outer product, this is giving us non-linearity. So V bar and V bar, both of them are the same quantities, and generally both of them are unknown quantities. Because of that, this is the nonlinear term. So convective operator gives nonlinearity to the Navier-Stokes equations along with the asymmetry of the flow equations. So when we handle these problems by using CFD treatment, one of these velocities, the first one, we treat it as a coefficient or a known quantity, and the second velocity, which is coming later, this we treat as the unknown or the degree of freedom. So the first part we treat it as known, and the second part we treat it as unknown. So the known part acts as a coefficient, and then it becomes a linear equation. It is reduced to a linear equation, and then we can use the linear equation solvers for this. Now, we mention the references which I have consulted for this class. So, first one is the classic text by Professor Patankar on CFD. So, in that, he has discussed the generic transport equation, and all these conservation equations can be derived from the generic transport equation. That is also available in the CFD book by Versteeg and Malala Sekera. So, I also recommend that the learners must consult the chapter of governing equations in the CFD book by Professor John D. Anderson. And regarding the finite element portion on the strong form, I have consulted the classic text of Professor T.J.R. Hughes and subsequently the text of Professor J.N. Reddy. So, for the FEM course, most of the times we shall follow the texts of Professor Hughes and Professor Reddy. Thank you very much for attending today's lecture.